quantum and polynomial time hierarchy.
Thank you, Avi. Thank you for the invitation to speak here. It's a great honor, and I'm glad to be back at IIS giving this talk. This is joint work with Ran Raz. He's now at Princeton University. And I want to start with a brief introduction, to complexity theory, to the famous complexity classes. So in complexity theory, we studied the power and limitation of computational devices with restricted resources, such as time, memory, communication. And we have complexity classes capturing this, efficient computation with limited resources. So we have P, which correspond to polynomial time, everything that we can solve efficiently in the length of the input. In particular, we can, for example, we can solve what is the shortest path between two cities. We can do it, compute it in polynomial time. We can solve linear equation in polynomial time. We can do a lot of stuff. Another famous class is NP, non-deterministic polynomial time. These are tasks that, given a solution, we can verify efficiently that this is a good solution. But it's not necessarily easy to find such a solution. In particular, one famous example is satisfiability. You're giving a formula over Boolean variables. You have ands and ors and nots, and you want to test whether or not there exists a satisfying assignment to this formula. So if you are given an assignment, checking it is easy. You just plug the values and check the value of the formula. But finding this assignment is known to be NP-complete. And we believe that this cannot be done efficiently. This is really the P versus NP question. It turns out there are a lot of natural problems that are NP-complete. And if you solve one of them, you solve all the rest. OK, so this is probably well known. So NP, you can think of it as saying that there exists some assignment that satisfies some properties. You can also talk about co-NP, which asks whether all assignments satisfy some properties. And you can even go higher than that and alternate between quantifiers. Say that there exists some x, such that for all y, there exists some w that satisfies some properties. And this would give you the polynomial hierarchy. OK, when you do these alternating quantifiers. And all these complexity classes sit inside P space, everything that we can compute in polynomial space. OK, things that you can compute with efficient amount of memory, not necessarily efficient amount of time. OK, we can also discuss randomized algorithm. There, the algorithm needs to come up with the right answer with, let's say, high probability, 99% or even higher than that. And in the famous work of Miller and Rabin, they showed that you can check whether a number is prime or not with a randomized algorithm that runs efficiently. And it took nearly 3 decades to come up with a deterministic algorithm, the well-known AKS algorithm, that solves this problem. And in fact, by now, we have strong reasons to believe that P is actually equal to BPP, that you can de-randomize every randomized algorithm and find a deterministic algorithm that solves the same task. However, this is still an open question. And currently, we know that BPP is inside the polynomial hierarchy. This is our, at least with respect to this picture, this is the smallest class that contains it. OK, so now we get to the main motivating question. What is the power of quantum algorithms or quantum computers? So quantum algorithms that run efficiently are captured by this class BQP, bounded error, quantum polynomial time. And one famous example of a task that you can solve in BQP, you can solve using quantum algorithm efficiently, is factoring a big integer into its prime factors. OK, so this is the famous Shor's algorithm. And classically, we currently don't know how to do it. The best algorithm run in slightly sub-exponential time. So this seems that quantum gives you an advantage, at least in this task. So really, the question that we were motivating understanding is where does this BQP, where does efficient quantum algorithm sit within this picture? OK, so one thing that we know is that everything that you can do with a randomized algorithm, you can also do with a quantum algorithm. So BPP is inside BQP. OK, on the other hand, you can simulate any quantum algorithm using polynomial space. So BQP is inside P space. So it's somewhere in this picture, but we are not sure what is the connection with NP, PH, co-NP, and all these other classes. Okay? So this is what we know. BQP is between things that you can compute efficiently using randomized algorithm and things that you can compute with polynomial amount of space, but we don't know necessarily what's the connections between BQP and NP or BQP and PH. And we can ask in both directions. Maybe BQP is containing NP, maybe NP is containing BQP. Okay? The common belief is actually that none of these containments is true. None of these conclusions are true. So we believe that there are some tasks that quantum algorithm can solve efficiently that are not in NP, and some tasks that are in NP that quantum algorithms cannot do, and same goes from PH. Okay, so let's say that this is our belief, and this is what we try to do. Can we prove it? Well, proving such a statement would also prove that P space is different than P, because all of them sits inside P space, and all of them contain P. So this seems like a huge open problem in complexity that we are very far from solving, and we are not going to do it in this talk. Okay, so just to make clear, this entire picture, it's still consistent with our current knowledge that all these classes are the same and that they are equal to P. So maybe P equals NP equals PH equals P space equals BPP equals BQP. Okay, we have no proof that this is not the case currently. Okay. So what do? It seems that we are stuck. We believe something, and it seems that we cannot prove it. So what we do is we relax the question. Okay? And we'll relax the question by turning to an oracle. So what is this oracle? An oracle is sort of like a magical black box. You can ask their question, it will give you answers. But these answers not necessarily would solve the problem, the task that you are trying to solve. So it could be just hints that may or may not help you solve the task that you want to solve. And you can think of this oracle as another resource. So you can think of the resource of time, the resource of memory, and you have also the resource of the oracle, how many times you can ask the oracle question.
What kind of questions are you allowed to ask the oracle?
Okay, so it will be very sort of formal and a bit weird. So you just ask him a question, and he tells you a yes or no answer. And the question is whether or not this oracle would help you solve a problem. So let me give you some examples that show you that it gives you some power. So let's say the oracle can solve SAT, satisfiability. Then a polynomial algorithm with an oracle access to that can ask questions to this oracle can solve all NP complete problems, right? Because you can do a reduction between any complete problem to SAT, and by asking the questions on SAT, you can solve any problem. So you can solve traveling salesperson, you can solve what is the maximal click in a graph, and all these questions if you have an oracle to a SAT. So this is one example.
Oracle as many times as there are input to the SAT question?
You can ask. So okay. So how do we count things? So when we ask the oracle a question, the oracle would give us an answer within 1 second. So we think of it as if within like one time step, but we still need to write the answer down. So if we have a polynomial time machine, we cannot ask questions that are longer than polynomial in the length of the input that we are given. Okay, but the oracle would answer sort of immediately. Okay.
An oracle is a function.
Yeah, you should just think of it as a function. Sometimes the function helps solving a problem, sometimes it doesn't. So basically, yeah. So we are trying to separate classes, and we will separate them relative to an oracle. So we would show that relative to an oracle, let's say NP can do stuff that P cannot. Okay, so you should just think of it as if we are trying to compare. Okay, so this is an analogy from Terry Tao's blog. So he said, let's say that you want to compare two students. Let's call them P and NP. Okay, and it's hard to tell. You want to say who is wiser than the other. Okay, so you want to. Okay, so one thing that you know is that everything that P can do, NP can do. Okay, but maybe it cannot do more than that. And then without any help, you cannot separate the two. Basically, both of them with papers, they're sort of lost in their way, so that the students, so they need a little bit of help. And then you give them like a supercomputer. Think of the supercomputer as Oracle. And then you suddenly see that NP is starting to generate a lot a lot of papers, a lot of results, and P is still stuck. So then you say, okay, so this is some evidence that NP is wiser than P, although it doesn't necessarily tell you what would be the situation without the access to this supercomputer or this oracle A. Okay, so this is maybe a good analogy. Okay, so let's be a bit formal. What is an oracle? It's just a function or a language. So you give it any string in 0, 1 star, and it just tells you yes or no. Okay, so this could be useful or not. And now you can define, with respect to any oracle A, you can define analogs of these complexity classes. So for every class, P, NP, CoNP, PH, P space, you can define P to the A, NP to the A. What are these classes? These are the same computational devices that we talked so far, but they have new resource, which is access to this oracle A. So they could ask questions to the oracle A. In particular, let's see an example. So how can we characterize languages that are in polynomial in P, in polynomial time? We can say that a language is in P if there exists some Turing machine running in polynomial time that can decide whether or not some input X is in the language or not. Okay, so this is just a definition of P. And let's see what's the definition of P to the A. It's very similar, but the Turing machine can have also access to the oracle A. It has an additional tape where it could write the question to the oracle, and then it could say, now I want the oracle to answer me, and then in the next step, it will get the answer. Okay? And as we saw, sometimes this gives you more power. Okay. So it turns out that when we relax this question of separating with respect to an oracle, we know a lot of separations. So in particular, all these classical classes that I mentioned, P, NP, PH, P space, can be separated relative to an oracle. So you can show that there is an oracle such that P to the A is not equal to NP to the A. This is the seminal result of Baker, Gill, and Solovay. And in the same works, they prove that NP is different than CoNP, which also implies that NP is different than PH. And then in this line of work, started with the work of first Sachs and Zipser, and finally Yao proved this result. You can show that PH is strictly contained in P space relative to an oracle.
So it's a bit confusing. So the operator is something to the A is not for the set of languages. It's for some definition of the set of languages.
It's for the set of machine.
Y doesn't mean that X to the A is equal to Y to the A.
Exactly.
Otherwise this would all imply.
Good point. Good point. Yes. So this is a bit of a bad notation because it could be the case that X equals to Y, but X to the A is different than 1 to the A. And there is even an example like that. IP equals P space. There is an oracle where IP to the A is not equal to P space. So this is sort of like a proof that doesn't relativize. But there are a lot of proofs that do relativize. There are inclusions or separations that work with respect to every oracle. So this you can see it as some weak evidence about the true relation between the things. But you are correct. It's not a strong evidence. We have an example. In particular, we also have oracles where P to the B equals to NP to the B by the same paper. This sort of tells you that oracles sort of.
The statement means that there are oracles that answer useless questions. What does it mean?
The first result shows that there's an oracle that is useful.
Yeah, but the useful oracle might depend on the question you're asking, I assume.
It's up to you which questions you ask. It's overall the questions that these machines, given their resources, could ask. So in the best utilization of A, the important thing is that it's a fair game. Both machines you want to separate get access to the same oracle.
Okay. So the last statement meant that there are some oracles that are useless regardless of the question, I guess.
It can be. Can be. The oracle that answers 0 always is a useless oracle.
Yes. So we can sort of, you can also think of this as like some step along the way to prove P not equal to NP. So if you could make this oracle A weaker and weaker, and in the end that it would just give you like the constant function, then you would prove that P is not equal to NP maybe. But I'm not sure. Yeah, but sometimes the oracle is so strong that it could help both P and NP to do stuff that are equal. So if the oracle is sort of in P space, let's say, then P to the A and NP to the A could be equal to P space. So this is one example where you can show equality under oracle. Okay, so as I said, it gives you some evidence about the true nature of the problem, but not a strong evidence. Okay, what about quantum versus classical? So in this seminal result of Bennett, Bernstein, Brassard, and Vazirani, they gave an oracle such that NP can solve problems that BQP cannot. So there are some tasks in NP that quantum algorithm cannot. In fact, the quantum algorithm would need to run in time which is exponential, 2 to the n over 2, which shows that Grover search is tight. Okay, Grover search can take anything that can be solved in NP, anything that you can sort of like only search for a solution. It could search a little bit more efficiently, so by square root of 2 to the n. Square root of going over all possibilities. And this shows that you cannot even improve that. Okay, and you can see it as evidence to the fact that quantum algorithms are unlikely to solve NP-complete problems. And this is a common belief in the quantum complexity community. On the other hand, we can show that quantum algorithms have advantage over classical algorithms. There is an oracle where BQP can do stuff that BPP cannot. That quantum algorithm can do stuff that randomized algorithm cannot. This is in the seminal result of Bernstein and Vazirani that actually founded this field of quantum complexity theory and defined BQP, and they had a lot of interesting results in this paper. Okay, and this for the same oracle on the same task, it was shown that BQP to the A is also not in NP to the A, and even you can sort of take a combination of both randomness and non-determinism called MA, and you can show that it's even not in MA. However, after all these results, it was still open whether BQP is inside PH, or so this is now, but whether or not this holds for any oracle. Okay, so one thing to say, so if we can prove the fact that some class is in some other class in sort of a black box fashion, so we can sort of simulate one by the other in a black box fashion, this would also translate to all oracles. This would be a statement that is true for all oracles. So showing that, let's say, BQP to some oracle is not in PH to some oracle means that if this is true in the real world, the proof for this would not be a simple proof. It will not be some simulation. Yes.
So for the quantum model, the oracle is still classical, right? It's the same, or is it also you can ask?
Function.
Yeah.
Can you query the superposition or not?
Yes. That's very important. You could query the oracle in superposition, but the oracle, you should think of it as a function.
Okay, but it's not the same oracle. You can get more of it in something.
Yes. Yeah.
So when you can guess, you get more. It's the machine can do whatever it's allowed to do.
Right. So also in the randomized algorithm, you can think of it, right? So you have some randomized, and then you are sort of asking a randomized query. So it also can allow it more. So it's a fair game. It's like a
The machines are different, but the access to the oracle is do whatever they can do.
Yeah. Okay. So now we get to our main result. We show a separation between BQP and PH. Just to be formal, let's define PH slowly. So we say that a language is in this polynomial hierarchy, or PH, if there exists some constant k and some relation r that can be computed in polynomial time, such that you can express whether or not some string x is in the language L as this formal quantified formula. There exists some string y1, such that for all strings y2, there exists some string y3, and you do it k times. You alternate between exist and for all. And then you take the relation r on x and all the y's. So just let's see an example why NP is inside PH. So in NP, we just take one quantifier. There exists some y's such that the relation on r on x and y holds. CoNP asks whether for all strings. So we would only use this quantifier. And basically, pH allows you to do more than that. So you can sort of use more than one quantifier. So what do we want of this expression? We want the number of quantifiers to be a constant, and we want the size of the strings to be polynomial in the length of x. Okay, so this is the definition of a polynomial hierarchy. And our main result is we show that there exists some oracle and a task that can be solved using quantum algorithms with access to this oracle A. Yes, in superposition, as the Fs asked. However, a pH machine with oracle access to A cannot solve this task. Okay. In fact, the result is stronger than that. So here the definition allowed for a constant number of quantifiers. We can even go to the number of quantifiers which depends on the length of the input, even almost up to linear, something like the length of the input divided by log the length of the input. Alternatively, we can take these strings y to be of nearly exponential size, and the result would still hold. So the result is actually stronger than stated here in this slide. I want to interpret it, quoting Lansford now, who commented on this result. He says, even if P were equal to NP, even in a world where P equals to NP. So when P equals to NP, it turns out that the entire polynomial hierarchy, the entire thing that you can do by checking whether there exists something for all something, this entire thing can be calculated in polynomial time, which seems highly unlikely. But even in this world, there would be some things that quantum algorithm can do that classical algorithms cannot. Okay? And in fact, he made this statement more precise. He actually showed an oracle such that P to the A equals NP to the A, but BQP is not inside P to the A. And in order to do that, you need to modify our oracle a bit. So this only tells you that this is possible, but he actually made it, he proved that such a thing exists. You need to modify the oracle. Okay, so we talked about oracles a lot, and this was maybe a bit confusing. Oracles are, you can also think of them as sort of like a black box setting. You're sort of want to understand something on a huge string, and you are allowed the black box access to it. You can ask what is the value of the string on this location, on that location, so on and so forth, and you need to sort of figure out something about the string. And there are a lot of connections between this black box setting or query model and oracle separation. And in fact, we will soon use this reduction and move to a question about pseudorandomness. Okay, so from now on, we will talk in the language of pseudorandomness. What is pseudorandomness? Okay, so you can sort of like forget about oracles for a second and just look at this slide. So you have a truly random string here. You have coin flips. Each of them are gold, are truly random. Each heads with probability half, tails with probability half, independent of one another. Everything is good. On the left-hand side, you have something which may not be truly random. So maybe you have some biases or correlations, but we say that it looks random. What do I mean by that? To the function operating on this sequence of coins, this string and this string looks the same. So
distribution and this distribution.
Yes, these distributions look the same. So let's be more precise about it. We say that the distribution D, so think of this as a distribution D, is pseudorandom against a class of functions C if any function in this class has similar expectation on the distribution D as it has under the uniform distribution. So the expectation or the probability of acceptance under D is similar to the probability of acceptance under the uniform distribution U. So we will talk about Boolean functions that only output one bit, and then expectation sort of captures everything that we want to say about the function. Or at least the output distribution of the function. Okay, so how should you think of it? You should think of f as trying to tell the difference between this distribution and that distribution. And it sort of wants to say that here it's 0. It wants to say here 0 and here 1. But then it would fail. Why? Because the expectation under the two settings is similar. So it cannot answer here 0 with high probability and here 1 with high probability. If it will answer here 0 with high probability, it will also answer here 0 with high probability. Okay, so it cannot tell them apart. Okay. So now I want to tell you about the beautiful reduction of Aronson and Pfefferman et al. They pose this following challenge in pseudorandomness and show that if you can solve this challenge, you would get an oracle separation between BQP and the polynomial hierarchy. And what is this challenge? They ask, can you find a distribution which looks random for constant depth circuits? And we will see the exact definition of what do I mean by constant depth circuits in a bit. However, this distribution does not look random to very efficient quantum algorithm. Quantum algorithm that runs in time which is logarithmic or polylogarithmic in the length of the string. So again, here it will be very crucial that the quantum algorithm can make queries to this string in superposition. So it has some random access to this long string, and it can in one time step, it can perform a measurement. It can sort of do a query in superposition over all possible locations. Okay. So this seems like maybe a bit mysterious, but let me demystify it a bit. So AC0 and the polynomial hierarchy are very related. So from the early 80s, this AC0 class was actually defined in order to study the polynomial hierarchy with respect to oracles. So what is the usual conversion? We saw that how to represent a language in the polynomial hierarchy. We have these quantifiers. We can take this quantified formula and turn it into a circuit. So we will replace every there exists quantifier with a huge OR. We will replace every for OR with a huge AND. And basically, on the leaf, we'll have some queries to the oracle. So we will represent them by variables. OK, so maybe let me draw some pictures. So let's say that I have some formula. There exists y1 for all y2. So I will replace this thing by a huge OR going over all possibilities for the value of y1. And then I will replace this quantifier by a huge AND going over all possibilities for y2. OK, so this is a conversion. And basically, if I have k quantifiers, I will get to a circuit with depth which is k or k plus 1 or k plus 2. Okay, something like that. OK, so from now on, we will focus on this question. Can you find a distribution that looks random for AC0 circuit, but doesn't look random for quantum algorithms, for very efficient quantum algorithms? OK. Good. So I want to state our main result in this language. We say that an algorithm has advantage alpha if alpha captures the difference between the acceptance probability of the algorithm on the distribution D and the uniform distribution. So basically, pseudorandom distribution with respect to algorithm alpha would say that with respect to this algorithm A, would say that alpha is small. OK. So what is our main result? We present a distribution such that there exists a super efficient quantum algorithm running in logarithmic time. The distribution will be over strings of length n or 2n. Okay. This super efficient quantum algorithm would distinguish between the distribution D and the uniform distribution with advantage which is 1 over log n. Okay, so this is not so small. On the other hand, we will show that constant depth circuits of polynomial size or even quasi-polynomial size can distinguish between these two distributions with advantage which is at most 1 over square root n. Okay, so you can see that there is a big difference between the advantage of the super efficient quantum algorithm and the advantage of a shallow circuit. An exponential separation even is the advantage.
How does the depth of the circuit affect? Is that hidden in the O?
Yeah, so it's sort of like hidden in this field. So basically, we would have something like log the size of the circuit raised to the depth of the circuit hidden here. So if the size is polynomial and the depth is a constant, this is something like log to some constant. So it's sort of negligible compared to everything else.
Don't you need to say how D depends on N for these statements to make sense?
What do you mean, D?
Well,
Yeah. So we'll present a distribution that works for every length of the input, which is a power of 2. We would present a distribution. And then all the statements are sort of held asymptotically. But the distribution would be sort of defined uniformly with respect to each input length. So you will see the definition of the distribution. It's not super complicated soon. I'm just saying that.
Since your statement only involves presenting a distribution, you don't need a general definition. You'll tell us.
Yeah, we have an explicit form of the definition of the distribution. So to be precise, I need to come up with a distribution for each input length or for infinitely many input lengths. Yeah, you are correct. Okay. So you might worry about this fact that this advantage is not a constant. Usually, we would want, randomized algorithm. We said that, or quantum algorithm, we wanted them to succeed with 99% probability. This only succeeds like with half plus 1 over log n. But there is a standard amplification technique. Just basically run it, several times and take the majority vote. This gets you from this advantage to a constant advantage, or even very close to 1, like 1 minus 1 over n. And this would only require you to run the algorithm sequentially, let's say, polylog n times. So this would still be fair for the reduction that we talked about earlier. The reduction we talked about earlier handle any polylog time algorithm, so it would still be okay. But I want to focus on this main result, and these standard techniques for amplifying are sort of standard, and I will not get into them. Okay. So let's talk about the plan for the rest of the talk. I want to first define this distribution D. It will not be an existential result. It will be actually an explicit form of a distribution. And then I will briefly tell you why quantum algorithm can distinguish D from the uniform distribution. And the main part would be to show that this distribution is random, or is pseudorandom, against AC0 circuits, shallow circuits. Okay, in fact, steps 1 and 2 were already given to us by Scott Aronson. So he suggested that this distribution showed that this distribution, quantum algorithm can distinguish between D and U. And he conjectured that this distribution is pseudorandom against AC0 circuit, but this remained open in his work. Pfefferman et al. That I mentioned posed a new candidate, another candidate that also satisfies these two, and it was still open to show this thing for their candidate. Basically, we are able to prove that the distribution that Scott proposed, or in fact a slight modification of that, and we will see that we need to modify it a bit, is pseudorandom against AC0 circuit, and the slight modification would not hurt this part. So this would be important. Okay. So let's start with defining the distribution. So the distribution is based on Aronson's suggestion for a distribution which he called correlation. Okay, recall that we need to sort of define a distribution over strings of length 2n, this is capital N. And for convenience, we'll think of this capital N as a power of 2. And we'll have some parameter epsilon, which is 1 over a constant times log n. You will see how it plays a role in this slide. Okay, so the first thing so we are trying to define a distribution D over Boolean strings. But the first thing that we'll do, we'll define a distribution over Gaussian. So we'll define a multivariate Gaussian distribution over the reals. And from this distribution, we would deduce the discrete distribution D. Okay, so how does the Gaussian distribution G looks like? We will first sample x1 up to xn independently IID from the Gaussian distribution with mean 0 and various epsilon. Okay, so all of them are independent. This is fairly simple. What's the next thing that we are doing? We are writing these x's in a vector and multiplying with the Hadamard matrix. Okay, the Hadamard matrix is an n by n matrix that is used all over the place. It's used a lot in quantum algorithms. You can, the nice fact about it is that you can compute this transformation super efficiently using a quantum algorithm. You can compute this Hadamard transformation in logarithmic time. And this would be crucial for the quantum algorithm. Okay, so you started with x1 to xn. You get a new vector y1 to yn. And then you simply look at the distribution of these x's concatenated with these y's. Okay? So this is a distribution over 2n numbers that have some connection. Okay? So if you know this part, this determines this part. And actually vice versa. The Hadamard transform is sort of similar, that you can also think of it as if you pick these guys and then compute h of these guys, it gives you these guys. Okay? Okay, so a little bit of calculation shows you that this distribution G is a multivariate Gaussian distribution over 2n dimensions, where the means of each coordinate is 0, and the covariance matrix can be written as this 2n by 2n matrix. You have an epsilon scalar multiplying the entire matrix. And you have a block of the identity, a block of the Hadamard, a block of the Hadamard, and a block of the identity. And this captures the covariances and variances between pairs of variables. Okay, what is this Hadamard matrix? In case you haven't seen it, the ijth entry of it is sort of plus minus 1 divided by square root n, where this plus minus 1 is dependent on the inner product of the two indices, I and j. How do we interpret I and j as inner product? So we just think of the binary representation of these indices, and we take the inner product modulo 2. Okay. So why the name for relation? This is also called the Fourier transform, and sort of it tells you, that x and y are correlated, but only after you apply the Fourier transform 1. So they are correlated. That's the name of score. Okay, so this gives you a distribution over Gaussian distribution. Now we want to get from it a discrete distribution. So we'll first sample z according to the Gaussian distribution. And then we get real numbers. So the first steps that we are doing is we'll truncate this number to be within -1, 1. If it's smaller than -1, we'll make it -1. If it's bigger than 1, we'll make it 1. If it's in between, we'll keep it as is. Now you will see how the parameter epsilon plays a role. So the variances of all these random variables are epsilon, right? 1 over log n. So with high probability, it will turn out that this truncation actually is doing nothing. Okay, so with high probability, all these coordinates will be within -1, 1 after we sample z from G. So this is actually the only reason to pick this epsilon. And then we still have real numbers between -1, 1. So we want to say how we get to discrete distribution. So we think of them as biases of coins, and we flip independent coins with these biases. Okay, so for each coordinate between I between 1 and 2n, we draw independent coin. Okay, with independent random variable which gets value either -1 or 1, whose expectation equals the value of zi. Okay, so let's imagine that z1 was 0. How would z prime 1 would look like? It would be just a random coin, just heads with 1 with probability half, -1 with probability half. The expectation would be 0. If the bias was, say, 1, then this z prime would be a deterministic value. Okay, so this gives us the distribution which is discrete and sort of is related to this Gaussian distribution. Okay, I want to very briefly give you some high-level intuition to what's going on. Why does the quantum algorithm is able to say that this distribution is not random, while the classical circuit cannot? So as you see, this distribution, let's talk about this Gaussian distribution. It has very small correlation between inputs. Okay, so between the left part, we don't have any correlation. Between the right part, we don't have any correlation. So the only correlations that we have are between the left and the right. And these correlations are small, are like 1 over square root n. Okay, we have something like n square of them. The quantum algorithm is able to take all these small correlations and sort of amplify them, accumulate them together to get a big amplitude. It gets a big amplitude, which is something like epsilon, or 1 over log n. We will see that classical circuits that are shallow cannot amplify these correlations. They sort of cannot accumulate small correlation together. This will be the crucial difference between the two models. Okay, this is a little bit high level. We will see more details in the remaining part of the talk. Okay, so now we get to this point where we argue that there exists some quantum algorithm distinguishing between D and U. As I said, this was already done by Scott Aronson, so I will just briefly mention the result. So both Aronson and then a slight modification by Aronson and Banis show that there exists a quantum algorithm that distinguishes between these two distributions and that runs in logarithmic time in the input length. Okay, so what is the statement that they showed? They show that for a fixed input x, y, so think of this as now as constant. The input is constant, and now you ask what is the probability that the algorithm Q accepts this input. So this is still a probability distribution because quantum measurements are random variables. So they show that the probability of acceptance is 1 plus phi of xy divided by 2, where phi is this expression. What is this weird expression? 1 over n to the 3 over 2, sum over I, sum over j, minus 1 to the I comma j, inner product of phi and j, so this should look familiar a bit, times xi times yj. Yeah, Scott calls this expression as measuring the correlation between the strings x and y, if you want an intuitive way to think about it. Okay. So I claim that under the uniform distribution, the expectation of this thing is 0, and the expectation of this thing under the distribution D is big, is like epsilon. So this is fairly simple to see just by this expression. So how can we see it? So just take expectation of this, use linearity of expectation, and just try to analyze what the expectation of each of these monomials. Okay, these are the only things that depends on the input, right? Xi, yj. When the input is uniform, xi and yj are independent, and each has expectation 0. They are like random plus minus 1 variables. So then you get 0 here. You sum all of them together, you get a 0. Under the distribution D, you have these moments, the expectation of xi, yj is not 0. How big is it? It's epsilon times this minus 1 to the I comma j divided by square root n. So the important thing is this plus minus 1 is multiplied with himself, and it gets to be a positive number always. And then you basically sum all of them together, you get that all of them are positive and all of them contribute, and you get an epsilon. Okay, so this is what I said, that you have all this more correlation and you can accumulate them together. I want to say that I didn't really tell you what the quantum algorithm is. It's not too complicated, but due to lack of time, I want to tell you more about the classical part. So one reason that you should suspect that this is a not so complicated algorithm is that it came alongside with the distribution. So sort of this is a distribution and an algorithm that are tailored to one another, and they both were suggested by Scott Aronson. Maybe I can just say briefly that the algorithm is sort of querying the string in superposition only once, and then is doing some linear transformation on the state and measure. And that's basically what you would get from this algorithm. Okay. All right, so we get to the main point. The main result is this is the fact that this distribution D is pseudorandom against shallow circuits.
The algorithm does a computation on the results. It's log n, so it's log n qubits. And
yes.
Polylog.
Right. So so you can think of them as log n qubits, or representing a state with n possibilities, and then you perform sort of the Hadamard transform on this set of qubits. Yes. Right. Okay. So the main result is to show that this distribution is pseudorandom. So I just want to recall briefly what are these AC0 circuits, shallow circuits. So as I wrote on the board, so these are circuits composed of gates, AND or gates. Each gate has many inputs. And on the leaves, you have either variables or their negations. Okay, so this describes some function, some Boolean function. And the two parameters to keep in mind is the size or the number of gates and the depth, the number of layers of gates that we have here. So in this case, the depth is 3. And we would focus on the setting of parameters where the depth is a constant and the size is n to the polylog n, or n to the log n, let's say. The reason that this is the setting of parameters that we are interested in is that this is what you would get if you translate pH to circuits. Okay, if you do this translation, this is what you would get. Okay, so these shallow circuits, we actually know and love them in circuit complexity because we can prove lower bounds to them. We can construct pseudorandom generators fooling them. So in this seminal result of Fursak, Sipser, Aitai, Yao, and Hastad, they show that parity cannot be computed in AC0. In fact, that parity, a very simple function, just computing the parity of the input, requires exponential size for constant depth.
Remind us what you mean by parity.
Parity is just like taking the sum of the input bits modulo 2. Okay, so checking whether or not the number of ones is odd or even. So you have like a huge string of length n, and you want to compute whether or not, the sum of xi modulo 2 is 0 or 1.
Wait, I'm confused because you can do that in n steps. Oh.
No, but you have a shallow circuit.
You have a shallow circuit. You need to do it in this model, not using an algorithm. Yeah, it's very simple to do it using an algorithm. That's the point, actually. It shows that this class is weak. It cannot even compute a very simple function, which is a parity function. Okay, so if this class is weak, what's the problem? We just need to show that this distribution fools this weak class. Okay, I want to mention also that this result that parity is not in AC0 as an application, they show that there exists some oracle that P space is not in pH. So this is actually this result that I mentioned earlier. And this actually motivated the definition of AC0 and the study of AC0. So before this paper, there was no sort of AC0 circuits. Okay. So there are a lot of proof of this fact. I want to mention one proof technique. How can you show that parity, this simple function, cannot be computed by shallow circuits? So using this seminal result of Hastad, in this beautiful result of Lineal, Mansour, and Nissan, they show the structural result. The shallow circuits can be well approximated by low-degree polynomials. So I need to say in which sense. So you can approximate this circuit using a multivariate polynomial that approximates it well with respect to the L2 norm. And this polynomial is over the real numbers. Okay, so we think of these circuits as computing like functions over the reals. Okay, so this is the main result, and the simple result is that parity cannot be approximated by low-degree polynomials. If you want to even approximate it slightly, you need degree which is n. And here the degree is like polylog. So you have a big difference between the two. And basically,
noting that in your plus minus one notation, parity is simply the product of all inputs, which is a degree.
Right, exactly. Yeah. So we are moving. Yeah. So we are actually thinking of like Boolean things as like plus or minus one, and then parity is just the product of these variables. Okay. So if parity cannot be approximated, AC0 can be approximated, this means that parity cannot be computed by AC0 circuit. In fact, it cannot even be approximated by them. So we can try to take this technique and apply it to our case. But then we are facing a wall. We are facing an obstacle. What's the obstacle? So we want to separate very efficient quantum algorithm from shallow circuits. However, for any quantum algorithm that runs in logarithmic time, So we think of this, we call this BQ log time. It can be well approximated by low degree polynomial. This is this famous result of Beals et al. That sort of expressed quantum algorithm in the language of polynomials, and this gave a lot of ways, it gives a new way to prove lower bounds against quantum algorithm. So it tells you, okay, so first of all, you cannot do parity. You cannot take parity because parity cannot be solved using very efficient quantum algorithm. In fact, sort of anything that you can do with a quantum algorithm has a low degree approximation. So it seems that the language of low degree approximation is the wrong language to separate these two classes. However, we were still persistent. We say, okay, let's try, let's try anyway. And we realized that there is a difference. Okay, so both models give you low degree approximations, but these low degree approximations are of very different flavor. Okay, so in particular, this BQ log time have low degree approximation, but they could be really dense. So in particular, if you remember this polynomial that we saw before, so notice that it's actually a polynomial of degree 2 in the input variables, right? In the variables x and y, this is a polynomial of degree 2. However, it has n squared terms, which is really dense, and you cannot approximate it using a sparse polynomial. On the other hand, shallow circuits, not only do they have low degree approximation, they have sparse low degree approximation. If you look at how many coefficients you have of sets of degree k, you have something like polylog n raised to the power k. And this is really this notion that I mentioned, that it cannot accumulate correlation. This is sort of capturing this. This fact that this is sparse tells you that you cannot amplify in some sense.
This polylog k is out of n to the k.
Right.
Log n to the k instead of n to the k.
Right. Great point. So how many sets can we think of? So without loss of generality, since we are talking about Boolean functions, these are multilinear polynomials. And then for degree k terms, there are n choose k of them, and we are actually showing that you can approximate it using polylog n to the k. So much smaller than that. Yeah.
So it seems like you don't have enough degrees of freedom even to describe the circuit. Does it mean that just bigger circuits are kind of complete similar functions somehow? Is like a DC dimension?
So for one thing is that you can sort of learn them efficiently, right? So this is this linear Mansur-Nissan. So I guess that, yes.
Is the DC dimension somehow similar, closer to this?
I'm not sure. I'm not sure about the VC dimension. I'm not super familiar with the VC dimension of these circuits. But based on this result, you can sort of learn circuits under the uniform distribution efficiently. We don't know how to do it under arbitrary distribution. This is actually considered to be hard. Even DNFs is considered to be hard. Okay, yeah, I see that I'm running out of time, so maybe I will just briefly tell you how do we use this result. Okay, so the first attempt is to, and by the name it will fail, and then we will need to fix it. So the first step is to use this and try to straightforwardly show that the distribution is pseudorandom. Okay, so I'm going to use this well-known and widely used Fourier expansion of a Boolean function. This basically allows you to take any Boolean function and express it uniquely as a multilinear polynomial. Okay, so you can write f of x as the sum over all subsets of the numbers 1 to 2n. You have a coefficient for each subset, just a real number between -1, 1, times this monomial, product of xi, where I is in the set S. So what do I mean by this equals this? I mean that over Boolean values, they get the same. This polynomial and this function gets the same value. But now, when I write this function as a multilinear polynomial, it naturally extends to the real numbers, right? I can now also plug in values that are non-Boolean. And there is a nice interpretation of the value of the multilinear polynomial on a real vector z. Okay, so if we take a vector z with all the coordinates between -1 and 1, we can see that f of z is the expectation of f on z prime, where z prime is sort of the result of independent coin tosses with biases according to z. Okay? So one way to see it, so just think what happens if f was a single monomial. This is pretty simple because it's just using the fact that these things are independent coins. You can use the fact that expectation of product is product of expectation with independent random variables. And then in general, you can just use linearity of expectation because you have a sum of monomials with coefficients. Okay, so this gives us a nice interpretation of the value of this multilinear extension over non-Boolean inputs. In particular, what will be the value on the all zero input? Yeah. No, not necessarily zero, right? So let's take this definition. So what is this? The expectation of the f of z prime, where z prime is sort of random coin tosses. So it's really the expectation of the Boolean function on the uniform distribution. Okay, or if you want, you can look at it from this expression. All the terms are getting killed except for the empty coefficient. Right? The empty coefficient measures the expectation under the uniform. Yeah, okay. Good, okay. So basically, when we do that, we can move from trying to show that the difference between these two discrete distributions, D and the uniform, is small. We can replace this distribution D, we can replace it with G. Okay, so I'm doing it a bit quickly. Okay, so how did we sample from D? So we first sampled a Gaussian random variable, and then we sort of treated it we truncated, and then we treated it as biases of coins, and we sampled independent coins according to this vector of z's. So basically, by this definition and the previous claim, the expectation of f of z prime is the same as the expectation of f on the truncated version of z. Right, this is just following the previous claim and the definition. And by the fact that we say that this truncation is doing nothing with high probability, so with high probability that truncation equals z, then we can sort of say that this is almost equal. I mean, up to a small error, they are the same. And this requires some calculation, but it's pretty ugly, and I don't want to get into. Because you need to say what happens if it's not equal. You know, just to bound it also. Okay, so what does it give us? It gives us the fact that we can now sort of replace this guy with the expectation of f of z, where z is this Gaussian random variable, and we can replace this uniform distribution with the value of f on the all zeros input. And now it suffices to just replace these two things. Okay, I think I will skip some of the slides to get to the interesting part. Let's just say that if you do it straightforwardly, you would sort of face a wall, so you need an additional ID. Okay, so the additional ID is to think of this Gaussian distribution as a result of a random walk.
Not the Gaussian, the Fourier distribution.
But I'm now talking about the distribution G.
It's over the reals.
It's over the reals, yes.
It's not a Gaussian, it's something else.
It's a multivariate Gaussian distribution with a particular covariance matrix, yes. Correlation, yes. Okay, so the idea will be instead of understanding the value of the function f on z, so instead of thinking of sampling z at one shot, according to this distribution G, which is a multivariate Gaussian distribution with the covariance matrix according to this that we saw before, we can think of it. We can think of it as the result of a random walk, taking a lot of tiny steps. So we can sort of sample t vectors z1 up to zt independently from the same distribution G, take their sum and divide it by square root t. Okay? what would we get if you sample, if you take the sum of independent Gaussians or multivariate Gaussians, you get still a multivariate Gaussian. And you get that the mean is the sum of the means, the variance is the sum of the variances. So you would get actually that this has the same parameters as the original distribution. Okay, so it's actually distributed the same way. So it's a way to, so we can sort of like think of it, we are starting here, and then we are taking a lot of small steps, and we are reaching some point. This is equivalent to just take a huge step at one shot. But the nice thing about taking these many tiny steps is that we can sort of analyze what happens along each tiny step, and it's much easier to analyze that. This is based on this beautiful work of Chattopadhyay, Khatami, Husseini, and Lovett, who proposed random walks as a way to construct pseudorandom generators. Okay. Okay, so the idea would be, again, to sample these t vectors and to look at t+1 hybrids or partial sums. So the first hybrid, H0, would be just the origin, okay, the all zeros vector. And then between 1 and t, we would take hi to be the sum over z1 up to zi divided by square root t. Okay, so notice what is h1? It's just like the value of a single sample from this distribution G divided by square root t. So it's a much smaller vector than the vector that we started with. And we are summing t of them. All right. So what will be the idea? The idea will be to apply a hybrid argument or a triangle inequality argument. Yeah, I should mention. So if you take t to infinity and do it, this would give you a Brownian motion. So it basically gives you a way to analyze this Gaussian distribution as a result of a Brownian motion. We are picking t to be finite, but like something like n to the 100. Okay, so a huge parameter t. And then we are showing that the difference between each two, consecutive hybrids is very small. We are showing that the difference between hi and hi plus 1, the expected value of f on these two hybrids, is very small. It's something like polylog n divided by t times square root n. Why is this enough? If you do triangle inequality, you would get that the difference between ht and h0 is simply the sum of these things, which is at most polylog n divided by square root n. And this is exactly what we wanted, because ht is distributed according to G, and h0 is really the zero vector. So this is what we wanted. And let's do a proof by picture. So the first step, this failed attempt that I didn't show you. So doing a very simple Fourier analysis, the straightforward calculation would show you that this first step holds, that indeed these two things are similar, h0 and h1 are similar. And this would crucially rely on the fact that these shallow circuits have this sparse low degree approximation, that some property of the Fourier expansion. It turns out that only the coefficients of sets of size 2 in the Fourier expansion would take into effect. And this is because this vector is so small that sort of it kills off all the high degree terms. So yeah, this is a bit quick, I guess, for this short presentation, but maybe you can trust me on that. And then the remarkable thing is that there is a simple reduction between the ith step and the first step. And this is due to a lemma of Chattopadhyay, Khatami, Husseini, and Lovett. But in order to do this reduction, we are heavily using the fact that AC0 circuits are closed under restrictions. When we are fixing some of the input variables to, let's say, constants, so we are fixing, let's say, the third input variable to 1, the seventh to -1, and so on, we are still getting a shallow circuit. It could even be of smaller size and smaller depth, but we will not use it. We will just use the fact that the size is not bigger and the depth is not bigger, so we can sort of apply induction on this restricted circuit. Yes, so this is the idea, and it turns out that both steps are actually much simpler than all the failed attempts that we had before. So let me recap what we did. Yeah. We defined a distribution D based on a multivariate Gaussian G. We very quickly claimed that this distribution is not pseudorandom against quantum algorithm, very efficient quantum algorithms that runs in logarithmic time. This was already given to us by Aronson, and we used a slight modification by Aronson and Ambinis. And then our main course would be to show that this distribution is pseudorandom against shallow circuits. We sort of reduces the question about discrete distribution to a question about the Gaussian distribution and f on all zeros. And we wanted to show now that this is small, and we did it by thinking of this multivariate Gaussian distribution, or the Fourier distribution, as a result of a random walk making a lot of small steps, tiny steps. In order to analyze the first step, we use the fact that AC0 circuits are approximated by sparse low-degree polynomials. This allows us to show that this first step has advantage 1 over t times square root n. And then we use this lemma of CHHLs that showed us that the ith step behaves very similar to the first step, using the fact that this class is closed under restrictions. Okay. I want to finish with one open problem that I think is interesting. And that is to improve this result by showing a separation between very efficient quantum algorithm and shallow circuits that can also compute parity. So now I am allowing these gates to be either or, ands, or parities in the circuit. And this gives me more power. And basically, all the proof can be repeated, and the only thing that is missing is a bound of this form. We need to show that if you look at the Fourier coefficient of sets of size 2, so you have here n choose 2 such coefficients, you want to show that this sum of absolute values is at most square root n over polylog n. We are tentatively close to proving it. We can prove square root n times polylog n, so we are very close to showing this. And if you can show it, this would be sufficient for the proof to work.
What does this mean for complexity, or is it just
So you can think of what is the analog class. So what is the analog for this AC0 with parity gate? So I guess it's sort of like what you would get with these things, but you can also have like XOR quantifiers. And yeah, so it's like a less known class, but yeah, maybe BP with parity P, I think, is sort of captures this as well. Okay, but I think in the language of circuit, it's very well motivated, at least. In fact, in this joint work with follow-up work with Chattopadhyay, Khatami, and Lovett, we conjecture that this square root n over polylog n is not the right answer, that the right answer is polylog n only. So the same as we got for just AC0 circuits. And if this is true, in fact, even if this is true, we would get something. But if this is true, we would get something very impressive. We would get a pseudo-random generator fooling this class of circuit, AC0 circuits with parity gates, whose seed length, whose amount of random bits is only polylogarithmic. Currently, the state-of-the-art pseudo-random generator for this class requires linear amount of randomness. So this would be a huge improvement. It's also, you can also ask this question about low-degree polynomials over F2. Such a statement over functions f's, which are low-degree polynomials over F2. Is it true that their Fourier expansion has this nice property?
Low degree is
Polylog degree. Yeah, and we believe it. We can show this. Okay, we can show this if the circuit is sort of read once, if it reads every input exactly once. And we can also show it for the first level. So we can show it over the set of coefficients which are singletons, but we cannot show it currently on sets of size 2. So that's, I think, some evidence that this conjecture is true. But let me finish with that, and thank you very much.